The rough draft? Rough draft, I wanted to collect this week. But it's not worth any points. So if you don't have it done, it's not going to adversely affect your grade. But you should try to get it done. Whip out a rough draft, quickly. The final draft. The final draft is due next week, Thursday. The test is on Thursday, but I might, because the report shouldn't take you too long to complete. The report is just, all this stuff I talked about on the board, just write it in words, and that's adequate. Some people will do maybe 50% of the stuff I talked about, or 25%. But you might get some more time. The problem is that we're going to have a test all the time because we're breaking it up into chapters. And so it's hard to avoid that conflict. Like in Chem 1A, I would never do it because you did three chapters on a test or something. It's just too much. But in Chem 1B, you could have it. The reports and the exams due the same day. We don't have a test tomorrow. We have a test next week. Officially, the test is supposed to be on Tuesday next week. Well, that's what it's supposed to be, on Tuesday. But at the Mesa, I was trying to coordinate with Mesa, so I guess he's going to review some stuff. So we'll have it on Thursday. Chapter 15.
Only chapter 15?
Only chapter 15. Some of the chapter 15 stuff I'm talking about now in chapter 16.
So we would do lab and then have the test, or?
Yeah, right. We have lab first and then the test. We'll have about an hour and a half for the test. The report, though, I might make due later because I might have you try recrystallization. Some people didn't get such big crystals, so we can try it again and try to grow some bigger crystals. Some people did it already, the recrystallization, and they got some nice crystals. Okay, Anthony? No. Big crystals would be like actual crystals with faces on them that you can see, like a quartz crystal. Just try to grow bigger individual crystals. No, just whatever your crystals are, we can try to recrystallize it. Recrystallization is done for a couple of things. One, to grow bigger crystals, and two, to get higher purities. The more recrystallization steps you do, the general, the higher the purity. So we'll just do one recrystallization step. How do you know those crystals are the right stuff? How do you know that? Well, one thing is it's not new. People have made this stuff before, and they've taken some measurements, the properties. So you can compare. They know what color it is. And two, what if what you made is something new? Nobody's measured the properties. Nobody knows what color it's supposed to be. Nobody's seen it before because you're the first to have made it, these nice crystals, let's say. Then how do you know what it is? we want to know what it's made out of, right? And so how could you figure out what it's made out of? This is just review for Chem 1A, Chem 1A, Chapter 2.
Can you resolve this one?
That's something you could try. Like in Chem 1A, you did the sulfate analysis. That you mean like that? Figure out how much sulfate. It's possible. Take it apart and then see. Other ways?
You're trying to make it into something you already know. You can make it chromium, no chromium.
Yeah, you could do that. So look back at chapter 2 if you want some more insight into it. All right, other questions? No other question? Let's continue with the problem we left off with last time, which is the HCl. Actually, we finished it, right?
The HCl one?
The HCl one?
This one's kind of. You showed us doing it separately months ago.
Right, okay, we did it separately and then we combined the hydronium from each one. But that doesn't work, and did I talk about why it doesn't work? Let's talk.
Because they're very simultaneous.
Well, that's the way we're supposed to solve it, but why didn't just solving it separately? Like, for example, in the first equilibrium here, we end up with 1.0 times 10 to the minus 8 molar hydronium. And then in the second equilibrium, H2O liquid plus H2O liquid, it's hydronium plus hydroxide. We know this one. Actually, water, do we worry about pure liquids and pure solids in the ice table? No, I never worry about those because the concentrations of the activities never change. So we just completely ignore them, write the ice over here. And so at equilibrium, this comes out to 1.0 times 10 to the minus 7 molar. And hydroxide is 1.0 times 10 to the minus 7 molar. And so what I did is we solved these separately, and then I said, well, this is in the same beaker, so why don't I just combine the two hydroniums? And so I think that's what we did. We just combined these. We combine the two hydroniums and we end up with 11 points of 0 times 10 to the minus 8 molar hydronium total. That is, this is the hydronium that's produced from the HCl plus the hydronium that's produced from the water, right? Hydronium from the HCl is this. That's the hydronium produced from water, which is this. This doesn't work. Why? This doesn't work because of Le Chatelier's principle. Le Chatelier's, did I do this with the water well thing? Yeah. So if I add more water to one side, it's going to upset the equilibrium. And it's going to shift to reestablish a new equilibrium. And so if I add additional hydronium, now, since this is in the same beaker, this equilibrium here is going to see the total hydronium, that is the hydronium from this equilibrium plus the hydronium from this equilibrium. And so this is no longer the hydronium ion concentration. Really, what the hydronium ion concentration is 11.0 times 10 to the minus 8 molar. Is this going to still be at equilibrium? No. Is what Le Chatelier's principle says is if I increase the concentration of the product, then the equilibrium should shift, or the reaction should shift to the left to reestablish a new equilibrium conditions. In other words, if I increase the concentration of the products, Q increases. If Q increases, we expect reverse reaction to occur. All right, so what this does is this upset my equilibrium. This is no longer at equilibrium. If this is no longer at equilibrium, we expect a Le Chatelier's shift and something to happen. So let's try to figure out what we have to do. And the same thing goes here, except this is a very unique equation because of K. K is very large. What a very large K means is we just assume that this is a one-way reaction. So what we just did was we increased the hydronium a little bit because this is no longer the hydronium, right? The hydronium for both of these is going to be 11.0 times 10 to the minus 8 molar. So something weird happens about this. When K is very large, like this, without numerical value, then Le Chatelier's does not apply, or it has no impact on this equilibrium, because what's going to happen is we increase the hydronium a little bit, which increases our Q a little bit. So our Q increases a little bit, but when we compare our Q to our K, well, K is very large. And so even though we increase the Q, K is still going to be bigger, and it still wants to go to the right. And so what we see here is in these one-way reactions, these are not perturbed by Le Chatelier's principle. So our first one is okay, our second one got screwed up. Which brings us to how can we fix this? Well, the way we fix this is we have to solve both equilibria simultaneously, right, to a common hydronium. The common hydronium would satisfy both equilibria. Which means having to solve a system of equations simultaneously. And so this is what I call the simultaneous method. Must solve simultaneously. When we solve a system of equations simultaneously, the math becomes much more difficult. And we don't like doing much math, so we look for tricks to save ourselves from doing much math. You can try these. For example, you could try to solve stepwise instead of simultaneously. In fact, stepwise is our common fallback method. Most of the problems that we're going to solve stepwise because it makes the math much easier, and it usually works okay. And so what we're looking for when we're solving something stepwise is that, you know, we have different Ks, and the Ks are orders of magnitude different. And so, for example, if I have equilibrium 1 with a K value K1 and compare it to equilibrium 2 with a K value K2, we want orders of magnitude difference here. If there are more equilibria involved, you know, like K3, K4, you know, we want significant differences in the K values. And so when we look at the K values here, this is a pretty good candidate for stepwise because K in the first step is very large. K in the second step is quite small because it's only 1.0 times 10 to the minus 14. When we have the K's like this, you know, the K's are successively getting smaller by orders of magnitude, then what happens is successive steps do not perturb previous steps. If they do perturb, then must solve simultaneously. And so we're going to try solving this problem stepwise before resorting to simultaneous. And that's what you do for all the problems. You just try it stepwise, and if stepwise fails, then unfortunately you have to solve it simultaneously. But there's one more trick that we're going to learn in chapter 18, which might help us in that we won't have to solve it simultaneously. All right, so when we factor in the two equilibria, we see that the equilibrium concentration of the hydronium is changed, resulting in a Le Chatelier's style perturbation. There are going to be two types of Le Chatelier's problems that you're going to deal with. One is just qualitative, you know, just predicting what direction things flow. For these qualitative ones, you could recalculate Q, or you could just kind of look at it and try to figure out what's going to happen. So let's take a look at something like number 55. Continuous removal of one of the products of a chemical reaction has the effect of causing the reaction to go to completion. Explain this fact. So let's take a look at this reaction here. If we continually remove the hydrogen, what we're doing is we're just making the product concentrations low, right? Or the product pressures low. As we continually remove this, that means Q is always going to be too small, right? Because we aren't going to have enough, let's say, hydrogen. And so the reaction is going to continually shift to the right, you know, as Q tries to become K. And so that would be the explanation of that. You're continually perturbing it so that it can't reach equilibrium. Okay, we can represent the freezing of water at 0 degrees C as H2O liquid, density 1.00 grams per cubic centimeter, goes to H2O solid, density of 0.92 grams per cubic centimeter. Explain why increasing the pressure on ice causes it to melt. And so this system might be at equilibrium, but if you change the pressure, it's no longer at equilibrium. If you change the pressure, what happens is it's going to favor the more dense phase. And so if we increase the pressure, the net effect is it's going to be a Le Chatelier's perturbation, and it's going to shift the equilibrium to the left or to the right. So we look, what's more dense, liquid water or ice? Liquid water. And so higher pressure is going to favor the more dense phase, liquid water. Is this the behavior you expect for solids in general? No. Just for ice, because the liquid phase is more dense than the solid phase. But most other solids sink to the bottom of their liquid phase. So most other solids have higher densities than their liquid phase. All right, pressure might impact things as well as volume and concentration. So explain how each of the following affects the amount of hydrogen present. So we're looking at the amount of hydrogen.
So if it shifts left, the amount of hydrogen goes down. If it shifts right, the amount of hydrogen goes up. And so we just got to figure out, does it shift left or shift right? Raising the temperature of the mixture. If we raise the temperature of the mixture, you know, does it favor the endothermic reaction or the exothermic? And so when we look at the delta H here, the delta H is negative 150 kilojoules, so that's exothermic in the forward direction. And so if it's minus 150 kilojoules forward, then it's plus 150 kilojoules reverse. Right? And so raising the temperature favors endo or exo? Favors endo. The easy way to remember this is ice, you know, melting ice. Melting ice is endo or exothermic? Do you have to add energy or remove energy to get ice to melt? You have to add, so it's endothermic. And so melting ice, increasing temperature melts ice. Melting ice is endothermic. And so raising temperature always favors the endothermic direction. Decreasing temperature favors the exothermic direction. The endothermic direction is to the left, therefore shifts left. Introducing more H2O gas. If we introduce more H2O gas, we're making the reactants more concentrated. It's going to shift right. If this were H2O liquid, then it would have no impact. Because, you know, if I add more H2O liquid, let's say I have a gallon of H2O liquid and I add a half a gallon to it, does it make it more concentrated? No, it's the same concentration, and concentration is what impacts this, not amounts. C, doubling the volume of the container holding the mixture. When we double the volume, it favors the side with more moles of gas. And so when we look at this, there are 4 moles of gas here. That's solid, so we ignore it. There are 4 moles of gas here. So we have 4 moles of gas, 4 moles of gas. Doubling the volume is going to have no impact on this equilibrium. Adding an appropriate catalyst. Catalysts speed up both forward reaction and reverse reaction. So adding a catalyst isn't going to have any impact either. Let's do one more here. 58. In the gas phase, iodine reacts with cyclopentene by a free radical mechanism to produce cyclopentadiene and hydrogen iodide. Explain how each of the following affects the amount of HI. So let's just see, you know, shift right, shift left. Raising the temperature of the mixture. Well, when we look at the delta H, it's positive, so it's going to go right, which is going to increase the HI. B, introducing more C5H6. The C5H6 is product, so it's going to shift it to left, which is going to decrease HI. C, doubling the volume of the container holding the mixture. If we double the volume, the side that's favored will be the side with more moles of gas. So we have 2 moles of gas over here, we have 3 moles of gas here. And so doubling the volume is going to favor the right side, which is going to shift it to the right. You can also do this, you know, if you double the volume, you cut all the concentrations in half. You cut all the concentrations in half, you recalculate Q, now Q is going to come out too small. Whereas in the previous problem, here, we double the volume here, we cut all the concentrations in half, but you know the concentration is equal, 4 over 4, you know, it cancels, the effect cancels. Whereas here, the effect doesn't cancel because, you know, we cut these in half and we cut these in half. Well, this is a cubic, this is a square, and it's going to have more impact over here, cutting the concentrations in half. The impact is going to be adding an appropriate catalyst. We talked about that already. Catalyst is not going to change or favor, it just speeds it up. Adding an inert gas such as helium. If we add an inert gas such as helium, does helium play any role in this equilibrium? No. And so helium, we don't care. The equilibrium is just going to be by itself, isolated from the helium, even though the helium is in there because the helium doesn't have a direct impact. And so if these 2 equilibria had nothing in common, then we could treat them totally separate. We could just solve one, solve the other, and that's it. But since these 2 equilibria have something in common, we can't. They're tied together.
And so that's Le Chatelier's principle qualitatively. Now, how do we do Le Chatelier's principle quantitatively? Well, that's what we're going to do here for this problem. And so we're going to try to solve this stepwise. And if that works, it's great because it's going to save us a lot of math. And so let's see if it works. So in stepwise, you start off with the biggest K value. So what has the biggest K? Well, HCl. I call this acid hydrolysis, acid and water. It's going to form hydronium and chloride. Ka is my acid hydrolysis constant, but it's also called other things, and it's very large. And so the first step is the same. We'll just go 1.0 times 10 to the minus 8 molar. We're going to assume that none of the molecules have collided with water. Water is ignored in the base table. The change is going to be complete, so we're going to lose all of it because of our K. When we have a K value that's very large, we assume 100% reaction. Assume 100% reaction. We end up with plus 1.0 times 10 to the minus 8 molar. I don't have to have an X here because I already know it's going to be complete. And so we're going to end up with 0 molar, 1.0 times 10 to the minus 8 molar, and 1.0 times 10 to the minus 8 molar. Okay. All right, I call this step 1. Okay. And then I'm going to move on to step 2. Okay, what I'm going to do with step 2 are two different options here. Option one will be a Le Chatelier style calculation. And so in option 1, I have this. I have my H2O liquid plus H2O liquid. This is going to form hydronium and hydroxide. And in Le Chatelier's, this is at equilibrium. So I know at equilibrium I have 1.0 times 10 to the minus 7 molar. Did I already do this calculation or talk about it? Yeah. And the hydroxide is going to be 1.0 times 10 to the minus 7 molar. And so at 25 degrees C, not all water molecules have the same kinetic energy. Some are energetic enough to collide and react, and when they react, they form this concentration. So this is going to be the equilibrium concentration. It's stable. This is the rate of collision forward is equal to the rate of collisions in reverse. Okay, but now I'm going to perturb it by adding the hydronium from HCl. And so I get an additional 1.0 times 10 to the minus 8 molar hydronium. And so now it's no longer at equilibrium. I'm just going to call it the new initial conditions, which is going to be 11.0 times 10 to the minus 8 molar. And this is going to be 1.0 times 10 to the minus 7 molar. And so when I calculate my Q, now my Q is bigger than the K, and so it's no longer at equilibrium. If Q is bigger than K, I know the direction of the shift. The shift is going to be, we're going to lose product and gain reactant. The reactant is just pure water, so we don't have to write that in. So it's just minus and minus. We don't write the plus over here because it's pure liquid. And so at equilibrium, we're going to have 11.0 sub-zero, so you'd say minus x times 10 to the minus 8 minus x molar, and 1.0 times 10 to the minus 7 minus x molar. And so the reason I call this a Le Chatelier style is because we have a system at equilibrium, water, Kw, and then we perturb it by adding some product here, or removing product or whatever. In this case, we're adding product. And so that's going to sap the equilibrium. This is no longer at equilibrium, and it's going to reestablish to a new set of equilibrium conditions. This new set of equilibrium conditions, we have to be careful especially with homework problems like that. You know, the homework problems they say, what's going to happen to the concentration of this? You know, so I might ask you, what's going to happen to the concentration of hydronium? Well, does it go up or does it go down? Well, it depends on what you compare it to. So it's a trick question. What's going to happen to the concentration of hydronium at the end of this is this. It's going to go down from the perturbed state. So if I looked at the perturbed state here, the new initial, the concentration's got to go down. But if I compare the equilibrium here with our original initial, with the original equilibrium, then the amount of hydronium actually went up. Because we started off with 10 times 10 to the minus 8, and we end up with 11 times 10 to the minus 8. And so, on the one hand, the hydronium concentration increased. On the other hand, it decreased. So it depends on what you're comparing it to. Are you comparing it to our original conditions, or are you comparing it to our perturbed conditions? So you have to watch out. So let's go ahead and solve this here.
Professor, instead of comparing it to the 1.0 times 10 to the -7, why do you compare it to 1.0 times 10 to the -8?
Why do I compare it to this
To
or
that one.
this? This, I'm not comparing it to, I guess, you could compare it to this because this is the hydronium we get from HCl. And so based on, from the hydronium we get from HCl, it's going to go up. We could also compare it to that. And so when you get a question that asks what's going to happen to the concentration, you have to watch out because you have to understand what they're asking. What are they comparing it to? That's it. And so just watch out for that. Well, we know what Kw is. Kw you should memorize 1.0 times 10 to the minus 14, which is just equal to the hydronium ion concentration times the hydroxide ion concentration at equilibrium. And so this is just going to equal 11.0 times 10 to the minus 8 minus x times 1.0 times 10 to the minus 7 minus x. This equation is not too bad, right? What would you do with this? Well, you might try successive approximations, or you just get it into quadratic form. And then you have two options: just solve it by hand, or did anybody buy the calculator with a quadratic solver? Or you could use a quadratic solver on basic scientific calculator. So this is a Le Chatelier's style calculation. It's solve for x. I don't usually use this option here, option 1. Instead, I do it by option 2. Option 2 I'm going to write down here. Option 2. The way we solve it, option 2, is we do something called a reset, right? This reset is also called a common ion type problem. So common ion fits this type of form. For the reset, this is how I'll set it up. We got hydronium and hydroxide. I know the initial here is, this is 1.0 times 10 to the minus 8, or no, 1.0 times 10 to the minus 7 molar, 1.0 times 10 to the minus 7 molar. This is from water, H2O liquid. But what I'm going to do is I'm going to just reset it to the left. That is, I'm going to get rid of all the hydronium and hydroxide and just convert that to liquid water here. And so I'll reset this.
when I reset it, I'm going to get a new initial conditions. The new initial conditions will be from the initial amounts from water will be 0 molar here and 0 molar. And so in other words, I'm just going to get rid of all these. This is stoichiometric, there's no limiting reagent. And so I'm just going to convert all this. Well, if this is minus 1 times 10 to the minus 7, then this has got to be plus, right? But this is pure liquid, so we ignore it. And so it's just minus, minus. So do you see what I'm doing here? In other words, I'm just pushing all the atoms to the left. It doesn't matter because in the end, it'll equilibrate to the same equilibrium as long as the number of atoms stay the same. And so another way of thinking about this is I'll assume no collisions have happened between the water molecules yet. Nothing's happened, 0 and 0, and then I'll allow it to react. But now, when I allow it to react, it's not going into an open playground or open field. Now, what we have is we have some HCl there. And the HCl is present, and it's going to supply some hydronium. This hydronium is going to be 1.0 times 10 minus 8 molar. And so from step 1, I'm going to have 1.0 times 10 to the minus 8 molar. Hydronium and 0 molar hydroxide. There's no hydroxide from step 1. All right, this is called the common ion type problem. And so now I have my initial total. The initial total will be 0 molar hydronium from water and 1.0 times 10 to the minus 8 molar hydronium from the HCl gives me a total of 1.0 times 10 to the minus 8. The initial hydroxide is 0 and 0, which is just going to give me 0 molar. Here. I'm running out of room. We continue this here. And so here's my initial total, 1.0 times 10 to the minus 8 molar and 0 molar. Okay, so what I'm going to do is I'm going to allow the water molecules to react and collide. Obviously, I can't stop them. I mean, there's already reaction there. But for calculation purposes, I'm going to imagine nothing's reacted. And so now I'm going to allow it to react. It's going to be plus x and plus x. If this were pure water, I know what x is. If this were pure water, x would be 1.0 times 10 to the minus 7 molar for both of these. But this is not pure water. This is what we call a common ion. And what the common ion does, that is this hydronium, this is a common ion from step 1. That ion comes down to step 2. What the common ion does is it inhibits the forward reaction. It inhibits it in this way. You can kind of think of the common ion as a predator, you know, and the hydroxide as the prey. And so if you have common ion there, what it does is it doesn't allow you to form as much hydroxide here, because the hydronium loves to attack the hydroxide, and the hydroxide the hydronium. And so what happens is the more common ion we have, the more predator we have. And that's going to decrease the maximum population of hydroxide. So originally in pure water, we could get to a maximum population of hydroxide of 1.0 times 10 to the minus 7 molar. But now with all this hydronium in here, that population is going to be quite a bit smaller. And so we got to figure out how much smaller that is by calculating what x is. And so here at equilibrium, we're going to have 1.0 times 10 to the minus 8 plus x molar, and then x molar here. Okay, then we need to solve for x. And so we just plug it back into our k equation. We've got 1.0 times 10 to the minus 8 plus x times x. All right, what's one of the reasons we reset? One of the reasons we reset is to get rid of binomial, right? And because the more zeros we have initially, the fewer binomials we're going to have. And so here we reset this, we got one fewer binomial, how does the math look compared to the other one with two binomials? Would you rather have two binomials that you multiply out to the quadratic form, or one binomial? Obviously one binomial. And so a lot of people say, well, you know, what's the advantage of resetting? Well, it just makes the math a little bit easier. For some people, it's not a big deal. Two binomials are good at multiplying binomials out, even with lots of decimal places and keeping track of all the sig figs. You know, they don't need to do it. But you know, if there's a time crunch, then this is going to save you because this is so easy. You know, not only that, in the previous problem, could we use the simplifying assumption? Is it possible to use the simplifying assumption in the previous problem, that is, assume x is very small? It's impossible. Why? Because if you assume x is very small, then x is going to drop out from the entire equation. You can't solve for x, right? When you reset, is it possible to try the simplifying assumption here? Yes. In fact, we're going to try the simplifying assumption. You know, I have a good feeling about the simplifying assumption. The simplifying assumption says that, you know, x is going to be much smaller than our initial. X is small compared to the initial. Well, I have a good feeling because of the k. When you look at the k value, it's very small. And so that means we don't expect much additional product, right? I have a good feeling that the simplifying assumption is going to work. And I have a bad feeling it's not going to work. Why do I have a bad feeling it's not going to work? I have a bad feeling this might not work because the initial is so small. You know, what we want is we want to remove a drop. And this is going to be drops from a big swimming pool. But we're going to be removing a drop, you know, because it's small, from like a little puddle of water. So it's going to be much more significant. Do you see that? And so here, well, you know, I don't care. I shouldn't think about this too much because the simplifying assumption is easy and it doesn't take much time. And so I'm not going to speculate. Is it going to work? Is it not going to work? I'm just going to do it. If it fails, it fails. If it works, it works, right? And the reason I'm going to do it is because it makes the math so easy. And so when I assume this, then this simplifies to 1.0 times 10 to the minus 8 plus x is just 1.0 times 10 to the minus 8. And then this is going to be times x. And therefore, x is equal to 10 to the minus 14 divided by 10 to the minus 8, which is 1.0 times 10 to the minus 6. You see, so the math is quick, but we don't know if it worked or didn't work until we calculate the percent change. And the percent change must be less than 5%. And so let's go ahead and calculate the percent change. The percent change is going to be the change, which is x, divided by the initial, which is 1.0 times 10 to the minus 8. And so that's going to be 1.0 times 10 to the minus 6, divided by 1.0 times 10 to the minus 8 times 10 squared. And so this is 10 to the minus 8, this is going to be 10 to the positive 8, which is going to give us a 10 to the 4% change, which is too big. Way too big. And so unfortunately the simplifying assumption did not work, which means we have to use the quadratic. But compare getting this into quadratic form versus the previous. And so let me erase this here. Getting this one into quadratic form is a heck of a lot easier because we don't even have to multiply any binomials. This is going to be x squared plus 1.0 times 10 to the minus 8x minus 1.0 times 10 to the minus 14. And so by resetting the initials, you know, over here to 0 and 0, or trying to get as many zeros as possible, it saved us quite a bit of math because this is going to equal 0. Does anybody have the quadratic equation solver?
And so we could use a solver, or you could do it by hand.
We got 9.5. That's 10 to the negative 8.
9.51 times 10 to the negative 8. Okay, thanks. That's correct. 9.51 times 10 to the minus 8. So we go back over here, and then we recalculate our hydronium ion concentration. So this is going to be 1.0 times 10 to the negative 8 plus 9.51 times 10 to the negative 8. This is going to be 10.51 times 10 to the negative 8 molar hydronium. So when we look at the hydronium, the first term here, the 1.0, comes from our acid, HCl. The second term, 9.51, comes from water. Which one supplies more hydronium to the solution, the acid or the water? Well, the acid supplies 1, water supplies 10, almost 10. Water, most of the hydronium comes from water. In fact, if this were about 100%, then around 95% of the hydronium in this solution comes from water. Okay, this is why the pH was so messed up. Because if we did the original pH based on just the acid, the hydronium from HCl, you know, pH came out 8.00. All right, and then the hydroxide is going to come out to 9.51 times 10 to the minus 8 molar. And so one of the things we do is we double check the equilibrium concentrations. Double check. When we double check, somebody multiply it out? 10.51 times 10 to the minus 8 times 9.51 times 10 to the minus 8. That should give us a K.
So it's 10 to the 1 to the negative.
Yeah, 9.51 times 10 to the negative 8. What do you get? 9.995 times 10 to the negative 15. Is that close to 1.0? I want 1.0 times 10 to the negative 14. And it turns out it is, because if we go 0.999 times 10 to the negative 14, and we round it to 2 sig figs that we're allowed, it comes out to 1.0 times 10 to the negative 14. And so it double checks. That means these concentrations are at equilibrium. But it also means that that this is not the correct hydronium concentration here, because in our other equilibrium is in the exact same beaker, in the exact same water. And so our other equilibrium doesn't care that, oh, is this the hydronium from itself, or is that the hydronium from the water, or is that the combined? Well, this is wrong, because now it's going to be 10.51 times 10 to the minus 8 molar hydronium. And so if we have, the hydronium is a common species, and it has to be the same concentration in the same beaker. And so if we have a concentration of 10.51 times 10 to the minus 8 molar hydronium in this equilibrium, will it perturb it? Le Chatelier's principle says if we increase the concentration of the product, we should shift it to the left. But this is a special case where K is very large. When we see a K that's very large, it's a one-way street. It doesn't go backwards. And so it does not perturb it. And so what happens here is this. Stepwise works here. And when we look at a beaker, let's say this beaker were labeled 1.0 times 10 to the minus 8 molar HCl. What's in it? Well, when we do an inventory of the species, one of the species we'll look for are HCl molecules. How many HCl molecules exist? Well, none, because HCl is too strong of an acid to exist in water, right? And so all the HCl molecules are going to hydrolyze.
And so the concentration of HCl molecules is 0 molar. When I say that, well, isn't it 1.0 times 10 to the minus 8 molar HCl? Yes, that's the total content. The HCl is not the predominant species. The predominant species is hydronium. And so the amount of hydronium is this. Should we add these two together? No, we already added them. You know, we already added the two equilibria. This is the equilibria from step 1. This is the equilibria from step 2, going to a common hydronium. And so the hydronium ion concentration here total is going to be 10.51 times 10 to the minus 8 molar. The chloride ion concentration we can figure out. And so here's our final. Let's color our final concentrations here. Blue. Our final HCl concentration, our final chloride concentration. Those both end at step 1. And so chloride's 1.0 times 10 to the minus 8 molar. And then hydronium here, this is carried to step 2. We add step 2, and then we get the total. The total is 10.51 times 10 to the minus 8. And both of these should have the same hydronium ion concentration because they're both in the same beaker. So this is hydronium, which is going to be 10.51 times 10 to the minus 8 molar. All right, and one final species is hydroxide over here. Hydroxide isn't, well, actually it is present in pretty significant concentrations. The hydroxide is 9.51 times 10 to the minus 8 molar. This is close to neutral. It's close to neutral because the hydroxide and the hydronium are close to the same concentration. We can figure out what the pH of this solution is. The pH is going to equal the negative log of the total hydronium. Well, we know what the total hydronium is, so the pH is going to equal the negative log of the total hydronium, which is 10.51 times 10 to the minus 8, which gives us a pH of 6. We'll calculate it. 6.97. Give me, no, 6.97, give me one more digit. 8? Okay, we'll just carry. We were allowed 2 sig figs. Actually, 3 sig figs. 8.4. It's pretty close to the pH that we calculated when we just added the 2 hydroniums. But for other problems, it would be very far away, you know, if we solved it using the wrong method. So this would be the final answer here. So when we have multiple equilibria, we would like to do it stepwise, and that's what we're going to try first. So let's try another problem. Let me try number 89. 89, determine the pH of A, 1.0 times 10 to the minus 5 molar HCN, and B, 1.0 times 10 to the minus 5 molar C6H5NH2, which is called aniline, which is an amine. Let's do A. Let's do good morning. So 89A, we have HCN, which is an acid. Acids are going to have a Ka associated with them. This is the acid hydrolysis constant. The Ka we can look up in the book here. Appendix D has a bunch of Kas. Yeah. Lipstick acid. So these are in, it's like alphabetical order. Yeah. And so HCN, do you know what it's called?
hydrocyanic acid, or hydrogen cyanide gas. So if we look at hydrocyanic acid, it has a Ka of 6.2 times 10 to the minus 10. That's Ka, 6.2 times 10 to the minus 10. And then we have another equilibrium occurring. I mean, this is an aqueous solution. Can you ever stop the water molecules from colliding? No. The water molecules are going to be continuously colliding, and that's going to lead to Kw. Kw is a Ka, acid hydrolysis constant, for water. It's water plus water. And we know the number here, 1.0 times 10 to the minus 14. And so if we have these two equilibria, you know, we're going to try to solve these two stepwise. So we try to solve it stepwise. Which one should we start off with first? We should start off with the bigger K. And so starting off with HCN, Ka is acid hydrolysis. So acid plus water yields hydronium plus cyanide. The Ka is going to be the hydronium ion concentration times the cyanide concentration divided by the HCN concentration, and water has unit activity, which is just one. Its activity doesn't change. So we leave it out. So this is 6.2 times 10 to the minus 10. So what we're going to do is we're going to assume that none of it has hydrolyzed. Yeah, and so we have 1.0 times 10 to the minus 5 molar HCN. And so our initial here is going to be 1.0 times 10 to the minus 5 molar HCN. I know I have that total molarity of hydrogen, carbon, and nitrogens in there, but what species is present can vary. But you know, I'm neither going to create nor destroy. And so what I'll do here is I'm just going to assume that nothing has happened yet. No hydrogen cyanide molecules have collided with water. So water, just leave blank. Okay, then I'm going to say, okay, let's go ahead and let them collide. I don't know how many, because can I say all of it? No, because K is not large. If K is large, then I know how much I'd lose. But since I don't know how much I'll lose, I'm just going to call it minus X plus X plus X. And so at equilibrium, I'll have 1.0 times 10 to the minus 5 minus X molar, X molar, and X molar. Now I'll have to solve for X. So we solve for X. X times X is going to give us X squared up here, and we'll have 1.0 times 10 to the minus 5 minus X here. So, you know, I have a, you know, I just want to try the simplifying assumption because it doesn't take much time. But I have a good feeling it might work. Why? Yeah, I don't expect much forward reaction here. Look at the K, it's tiny. So I have a good feeling it might work, but I also have a bad feeling it might not work. It might not work because the initial's not so big. You know, the bigger the initial, like a swimming pool, huge swimming pool, then, you know. But if I'm losing a tiny bit out of a tiny bit, then that's a significant change, right? Tiny bit from a tiny bit. But anyway, let's just go ahead and try it. If I try it, I'm just going to assume X is much smaller than 1.0 times 10 to the minus 5. And so that means that this is going to be X squared divided by 1.0 times 10 to the minus 5. Which makes X so easy to solve for. So let's go ahead and solve for X. X is equal to the square root of 6.2 times 10 to the minus 10 times 1.0 times 10 to the minus 5 would be the square root of 6.2 times 10 to the minus 15. What does that come out to? 7.87 times 10 to the negative 8. So I just tried it to see what happens, but you know, the final judgment will come when we justify it by the percent change. So the change here is x over the original, which is 1.0 times 10 to the minus 5. So it's going to be 7.87 times 10 to the minus 8 divided by 1.0 times 10 to the minus 5 times 100%. So this is going to be 7.87 times 10 to the minus 3 times 10 to the minus 1. In other words, there's going to be 0.787%. 0.787%, is that okay?
Yes.
It's okay, but this is what I call kind of borderline, because it's starting to get higher. This is close to 1%. The closer we get to 5%, the more error we're going to introduce. But it's still well within. It's less than 5%, so it worked. It was okay. This saved us from having to do the quadratic equation. Even if it didn't save us from having to do the quadratic equation, it didn't cost that much time. So we did. All right, so from step 1, this is what I'm going to do. I'm going to write these in decimal form. So this is going to be 4 zeros, 1, 2, 3, 4, and then a 1 0. Minus x. X is 7.87 times 10 to the minus 8. So that means I'm going to need 7 zeros. 1, 2, 3, 4, 5, 6, 7, and then a 7, 8, 7. So let's add some more zeros here. So that's going to give me 10. Sorry, 10. It's going to be 3, 9. 1, 2, 9, 9, 0, 0, 0, 0, 0. Okay. We got 5 zeros, a 9, 9, 2, 1, 3. Is that what you guys got? Okay. Molar. So I didn't really lose much. Percent change was just 0.7%, 0.7 out of 100. Okay, over here for the x, this is just 7.87 times 10 to the minus 8 molar. This is 7.87 times 10 to the minus 8 molar. I don't stop here. If I were to calculate pH here, what would the pH be? Look at this.
$7.1.
7.1. If you get a pH of 7.1, it is, well, 7.1 is basic, just a hair basic. And so you're adding acid and you're getting basic, which means that's not right. It's not right because we're missing the hydronium from water. We have two ways to get the hydronium from water. We could do a Le Chatelier's, or we could do a reset / common ion. Basically, I'm never going to do it Le Chatelier's because it's too much work. I'm always going to do it reset. So this is step 1. For step 2, what I mean by reset, and Patricia doesn't use this jargon, but I will. What I mean by reset is just the initial conditions. We're going to assume that no water molecules have collided yet. Or even if we have water molecules that collided, obviously water molecules, you can't stop them from colliding, so they're going to be collided already, or there's going to be collisions already. And so we're just going to push that. Normally in water it's 10 to the minus 7 molar, 10 to the minus 7 molar. We'll push it all backwards. And so we're back at 0 and 0. That means we're going to add waters here, but since water is a pure liquid, it's not going to impact its concentration or its activity. So it's just going to go backwards. And so this is the initial from the water, and then we're going to add the initial from the HCN. The initial from the HCN means that we're going to take the hydronium that we just generated in step 1 and bring that to step 2. So the hydronium we just generated is 7.87 times 10 to the minus 8 molar. And then we have no hydroxide from step 1. And so now our new initial conditions are going to be 7.87 times 10 to the minus 8 molar and 0 molar. All right, now we're going to expect a change. And so this is 0, so the only way we can go is up. So this is going to be plus X molar, plus X molar. In other words, we're going to allow the water molecules to start to collide. Normally when water molecules start to collide, it makes 1 times 10 to the minus 7 molar hydronium, but in this case, it's not. It's not going to make 1 times 10 to the minus 7 molar hydronium, nor will it make 1 times 10 to the minus 7 molar hydroxide. It's going to make more or less than that, the normal amount. It's going to make less than the normal amount. The reason it's going to make less than the normal amount is because you think, remember, you think of this as a predator here. And so that's going to control the concentration of hydroxide. If this were 0, then there's no predator present, and then the hydroxide concentration can increase to its maximum in pure water, which would be like 10 to the minus 7 molar. Right? And since there's so much hydronium here to begin with, it's going to keep that concentration down. That's called the common ion effect. The common ion effect means we don't get as much forward reaction. It means we have inhibition of the forward reaction due to this predatory effect of the common ion. And so at equilibrium, it's going to have 7.87 times 10 to the minus 8 plus X molar, and then X molar here. All right, so we plug that into our KW expression, so we're going to get 7.87 times 10 to the minus 8 plus X times X. The same thing in this particular equation. I have a good feeling that X is going to be small. 1, common ion, right? So X should be small. X can't grow too big because of the predatory effect. 2, because K, K is very small. And so I have a good feeling the simplifying assumption is going to work. But I also have a bad feeling it might not work. The bad feeling it might not work is because the initial is very small. 10 to the minus 8 is a very small pool. And so here, well, I don't want to speculate. I'm just going to try it. You try the SA, and then this is going to equal about 787 times 10 to the minus 8 times X. So therefore, X is equal to, this whole thing equals 1.0 times 10 to the minus 14. And so X equals, can someone punch it out? Calculate. -7? Okay. So this is what we get, and then we need to justify it. So let's calculate the percent change. The percent change is going to be the change, 1.27 times 10 to the negative 7, divided by the original. The original is 7.87 times 10 to the negative 8 times 100%.
Professor, where do you get the 1.0 times 10 to the negative 14?
I've memorized it. There's a K for this one. It's KW. Is it looking good? No. This percent change is going to be way bigger than 5%. Which means that the simplifying assumption failed here, unfortunately. Well, that's all right. At least we tried, and it failed. So let's go ahead and use a quadratic. So it's going to be x squared plus 7.87 times 10 to the minus 8x minus 1.0 times 10 to the minus 14 is equal to 0. Then hopefully you have a solver. You can do these quickly on a standard calculator. For your A, B, and C. A's 1, B 7.87 times 10 to the minus 8. C is negative 1.0 times 10 to the minus 14. Which gives you an X value of 6.81
times 10 to the negative
10 to the negative 8. And so that's our X. The units over here. And so let's go ahead and recalculate our hydronium. Our hydronium is going to be the 7.87 times 10 to the minus 8 molar that we generated in step 1, plus the 6.81 times 10 to the minus 8 molar we generated in step 2. And so this is going to give us 8, 16, 14. 14.68 times 10 to the minus 8 molar. And so when you look at this, it looks as if about 50% of the hydronium came from step 1 and about 50% of the hydronium came from step 2. Do you see that? And so that means that we essentially kind of doubled the hydronium here. The hydroxide is just going to be 6.81 times 10 to the minus 8 molar. And so we need to double check this. So we double check this by multiplying these together and see, does it come out to 1.0 times 10 to the minus 14? So we double check the K. So can somebody multiply these two numbers and see if it comes out? 1.0 times 10 to the negative 14. Times 10 to the negative 14. So that's okay. That works. So this is the equilibrium concentrations here. But in order to do it stepwise, we have to check one more thing. We have to check to make sure that step 2 did not upset the equilibrium in step 1. And so what we need to do is we need to see here, if I essentially double the hydronium, because this is no longer the hydronium ion concentration, right? The total hydronium ion concentration is now 14.68 times 10 to the minus 8 molar. And so what I'm going to do is I'm going to double check this to make sure. Actually, did I double check the original? We better double check the original. Did I double check the original? No. Let's double check the original. That is, this times this, the original hydronium, times this, the cyanide, should equal 6 point, oh no, let me take that back. This, the hydronium, 7.87 times 10 to the minus 8, times the cyanide, 7.87 times 10 to the minus 8, divided by the HCN should equal 6.2 times 10 to the minus 10.
7.8, 7.8 divided by.
Yeah. Or just do 7.87 times 10 to the minus 8 squared, divided by 0.5999213.
$6.13.
6.13.
Yeah.
Is that what other people got? Yeah? What did you get?
Around 6.24 times 10 to the negative 12.
Did you carry extra digits in your calculator?
Yeah.
Yeah?
I saved it, I stored the number.
You stored the numbers? Maybe it's due to round off. But anyway, both of those, well, 6.24 is better because it rounds to 6.2.
6.13 is a little off, so I'd start to worry. But it seems to work out okay. So we were at equilibrium, right? The purple concentrations were at equilibrium, and now we just doubled the hydronium, essentially. Do you think we're still at equilibrium? No. In fact, if we were to recalculate our K with the new hydronium, it's going to be bigger. And so let's do this calculation here, using these concentrations. And so when we double check this K, it's about, it was 6.24 times 10 to the minus 10, which is good enough. But when we calculate the green ones and determine the K is going to be 14.68 times 10 to the minus 8 divided by 7.87 times 10 to the minus, times 7.87 times 10 to the minus 8 divided by this one. 9.9213 times 10 to the minus 6. What do we get? Okay, so that would be 11.7 times 10 to the negative 10 is too big, right? It's too big. Well, that's okay, because if we double the hydronium concentration here, you know what type of problem that is? It's a Le Chatelier's problem. And so if it's a Le Chatelier's problem, what we could do is we could do a Le Chatelier shift. It's going to shift to the left, so we could just do minus, minus, plus, plus, just plus, and then we could recalculate the equilibrium, right? But the problem is if we fix this one, then it's going to screw up that one, and we're in this endless loop. Do you see? We're going to be in an endless loop because we can't fix one without screwing up the other. If we can't fix one without screwing up the other, then we have to solve this. How? We have to solve this simultaneously. There's no way to solve it one at a time. And so step 2 screwed up step 1, basically. If step 2 screws up step 1, then forget it, because if we fix step 1, it's going to screw up step 2. And so it fails. This upsets previous equilibria. Therefore, simultaneous. There's one more trick we can try before simultaneous, but that doesn't come until chapter 18. And so we have to solve this by simultaneous. Unfortunately, the book didn't. The book made a mistake. You'll see it. So if you look in the answer key for this, it's wrong. Don't bother. And so how do we solve this simultaneous? Well, we have to solve it simultaneous to a common hydronium. And so whatever hydronium we get in step 1 has to match the hydronium we get in step 2. And so let's go ahead and write HCN again first. HCN plus H2O liquid, this goes to hydronium, plus cyanide. We're going to set up an ice table here. And then we'll have our water equilibrium. H2O liquid plus H2O liquid. This is going to give us hydronium and hydroxide. And so what we need here is we need the equilibrium hydronium that we get in here to be exactly the same as the equilibrium hydronium we get here. And it has to be because it's in the same beaker, it's in the same solution. And so these two
hydroniums have to be the same. Now, how do we set it up? How do we set up the rest of the ice table? Well, this is the way we set up the ice table. Normally we would do a step 1 and then a step 2, right? But what we have to do is we have to do them together. That is this. What we're going to do is we're going to say that the equilibrium hydronium concentration is going to equal the hydronium that we get from the HCN plus the hydronium we get from water. So this is the same. So unfortunately we have 2 unknowns, right? And if we have 2 unknowns, we need 2 equations. And so all we have to do is we have to figure out the 2 equations to solve for these 2 unknowns. There are different ways we could set this up, but let me just show you the way I would set this up. The way I'd set this up is, okay, we have hydronium from water, we got to figure out what the hydronium ion contribution is going to be. And so we're going to reset both of these. We reset it,